Welcome to Careless Coder, and I finally succumbed to the questions. This is Introduction to C64 Assembly. Motherfucker! Ever since I did the ARM64 assembly course, a lot of people ask me in the comments like, can you do C64 assembly? I want to learn C64 assembly. And I always was like, there is so many good stuff online already for that. There is no use to doing this. But frankly, projects that I'm currently on are not really IT and electronics related. So I figured this could be easy filler material, and I will cut away all the details that the other ones do. For example, Matt Haverman. Want a good tutorial? Look at his site or channel, it's really good. But I cut away the meat and I just dive straight in. So let's dive straight in. And even my errors will be in there, so I can create a video in like 30 minutes. So welcome to this Commodore 64 Basic Assembly course. We will go really quickly and we will skim over all the details that you can read all about. We just keep it to the core and we start by writing stuff to the screen. And we will be using Kick Assembler, so you need to install Kick Assembler. And there are many tutorials to install Kick Assembler for your IDE. I run it in Visual Code in combination with C64 Debugger, which I really like. And these sort of things like basic upstart and .const are actually Kick Assembler directives. So I said we jump in quickly, and we will, because we first start by setting up a constant to point to our screen memory. And at default, the screen memory at the Commodore 64 is at 400 hex. And the reason that you should always use constants, and usually you would put this in its own file that you include all over again, is that if you want to remap your screen memory, and in the Commodore 64 you can, you just need to update this value at one place and not update all your code. And then you already saw we have the basic upstart, and we point that to a subroutine. And we end this subroutine, return from subroutine, basically going back to basic. What this does is when you actually hand code your assembler, you will tend to put in sys and then the address where to start from. So sys 1000 hex, for example. And no, sys, and then it would be in decimal in basic. This does that for you automatically, so you don't need to figure out sys in hexadecimal and that value. And then we say where to start from, and let's start from 1000 hex. That's a very safe starting point. 1000 hex, 2000 hex, those are available addresses when you run with BASIC. And now if we actually compile this, that is with Ctrl-Shift-P for Visual Code and build and run, you will see it will start, it will load something here, load from, and it's done. But we have not done anything useful, but we see that we actually can compile and run stuff. Now we want to put something to the screen. So if we put something at address 400, it would actually, let's run this again, write something there. Oh, I accidentally quit it. It would write something in the upper left corner. So let's do that. How do we do that? We need to write to this memory address. We cannot immediately write to memory addresses. We need to use a register for that. And we have three registers in the Commodore. We have the A, that is the accumulator, yes. A is the accumulator. We have the X and the Y, those are index registers. When you do any form of arithmetic, you will always need the A register on the 6502. These days with newer CPUs, any general purpose register is mapped to the accumulator. And the old systems, no, they didn't. And let's indent this. So let's load in A the value that corresponds with, well, the character A, which would be value 1. So we couldn't do this hexadecimal, decimal, or even in binary. I believe that is B0, don't recall anymore, but you can do that in Kick Assembler. But if we do this, reset character 1, you would expect that now the value 1 is in A. It's not. This is the address 1, its contents will be put into A. So if in address 1, for example, is the value 254, then A will contain 254. But we want the immediate value 1 assigned to the accumulator. Now, immediate is the hashtag or the pound sign. The pound sign means this value needs to be loaded in the A. But now it's in A and it's still not put into screen address 400. How do we do that? We have the store A command for that. And we can say store A 400 and this will work. Let me demonstrate. It will now load it, boom, and there we have that A in there. I mean, easier hello world you cannot really get, right? 2 commands and we have an A on the screen. But this is not really neat because we took the effort to actually do something proper and define a constant, so we run it with the constant. And it has the same effect. It basically says, find what screen is and replace that in that code, and it does that. Why did it actually end? There we go. Yeah. Oh, I pressed the, the Q. Right, so we already have something written to the screen, but we want to create a loop to actually clear this. So let's first make a nice subroutine. Let's call this CLS for clear screen. Return from subroutine. And let's use jump subroutine to CLS and return from subroutine. This should still actually work. All we did is just create a subroutine. Yeah, there we go. So what we say is jump to subroutine CLS. Run this, and here is an RTS that returns from subroutine. So it goes back here, and here it returns from subroutine as well, so it goes back to basic. That is clean coding. And we do not want a 1 in there, but a 32, because that's a space, and clear screen is all spaces. And we introduce the next register, X, and we set that to 0. So in X is now the actual value 0, and we can actually do this as well. Say store whatever is in A, so 32, at the address screen with the offset X. So in this case, if we run it, it would just set that same value in 400. So let's write a B there for a change. So we have the same behavior. Whoop, there we go, we have a B. But we want to count this up. So let's do a count. Actually, we're going to count it down. That makes more sense. Then we have all the values, and I will teach you right away why this is important. No, let me first teach the increment X, because then I can also show the compare statement. But you will immediately see that if this is 255, we will not actually get here. So inc X or in X will increment the value that is currently in X. So it will be 0, 1, 2, 3, etc. And if we don't do anything in this case, it doesn't really change any behavior, as you can see. It will just write that B there and be done, because we still need to loop back. in this case, we need to also compare x with the maximum value, because otherwise it would probably loop forever. Actually, I can do this without in this case, but yeah, okay. We are learning here. So again, with compare, we have a compare y, CPY. We have a compare, that is the A. You would expect CPA, but that is inconsistent. It's called compare CMP, and compare X. And again, we can compare whatever is in memory. So in this case, we would check what is in memory location 255, which zero space, we'll get to there eventually. And what is stored in that location. That's not what we want. We want to actually compare it to 255. And then as long as it's not equal to 0, now what compare X does is basically it says, what is in X? I subtract this value. If it is 0, I set the status registers 0 flag to 1. And then I will, can in this case, branch if it is not 0. Branch not equal means the 0 flag is not set. So CLS loop. And we just do that here. CLS loop. And then when it is actually 255, so it would say 255 minus 255 equals 0. Then the 0 bit is set. So it's no longer, equal, yeah, and then we return. So now we will see a lot of B's there. A lot of B's, a BBB, BBB. But we only had, as you can see, we only have half the screen. Only 255 values, or even 254, because I think this one is incremented before, yes, and it falls through. So yeah, that's why this is a bad idea. So let's actually use it the way that I always use it, and that you should actually use loops in assembly. You decrement it, and what it does now, it will actually fill all 255. It's a bit of a cheat, but it will work. So it's first set to 0, so we write it on the 0 position. Then we decrement it, so it becomes 255. And then it's no longer 0, so it will continue to loop until it's actually decremented to 0. And then we fall through. That way we have all 255 characters. So if we run this, we have 255 B's, we have one extra. That one. And it is, it's more efficient because this compare X, I believe, is 2 cycles. And we run this 255 times. So we're saving 512 cycles. So that's quite a lot on a machine that only has 1 million cycles to waste to begin with every second. So this is the more efficient way. But now we also need to clear the rest of the screen. How do we do that? Well, we can use some compiler statements for this. So we can add 100 to it, because we know we have screen size is 40 by 25. That is equal to 1,000 characters. So we can add that. 200, 300. No, because then we would actually, if we run 300, it does work on the Commodore 64. Usually I cheat it like this. But we would actually run 24 bytes out of the actual screen memory. So what is a good practice is, it's actually 300 minus 24. And I calculated it here already. That is 2E8. Come on, click. Yeah. To E8. So this is the safe way. If we run this, we will have a whole screen full of Bs. There we go. And if we now change this B into a space, we created our clear screen. So 32. Run this. Why did it break? Sometimes that happens, yeah. Sometimes Kick Assembler misbehaves a bit. Control P, Kick, there we go. Or the plugin, I don't know which it is, but there we go. We have a clear screen. We wrote our first application, a clear screen, or whatever you want to put in it. So if you, for example, want to say it's not my clear screen, but I want it with all C's, then you can, because you can load A with 30. Actually, we parameterize it then. So let's remove this. Yeah. So we say load A with 3. Clear screen, or actually then it should be called fill screen, but who's counting? And then you passed your first parameter using a register. That is the easiest way to pass parameters, is using registers. And if we want to have it clear screen, we can use this. But since this is called clear screen, why not actually load A with 32? And this is what you see. You need to be aware what your functions or subroutines actually use for registers. In the next lesson, we will actually look at popping and pushing register to stack, because that is the next clean thing to actually do this. Now, I also want to instill on you the fact that we have kernel calls. We can use JSR $FF81, I believe it was. I hardly ever use kernel calls. C64 kernel calls. FF81, yes. So I was right. Close all. We can do this. So again, jump subroutine points to this address, because this CLS actually points to whatever address this is. So probably 1006, I think. And this also clears your screen, but then using the kernel. It's a tiny bit slower than this, but the great thing about actually using these kernel calls is that you have an easier time porting it. This is very specific to a Commodore 64, of course. And if you use the kernel calls and you use, for example, an Atari, then it would be easy to actually search and replace this value to whatever the Atari uses in order to clear the screen. So generally, in coding practice, when you don't need speed, the kernel calls are a better solution. And we can also do one more. Let's do a jump. Current address, I believe it's a minus. No, what is the current address? Star. And now you will see that it will jump to its own address and it will just stay completely empty. It will never go back to basic. It cannot go back to basic. So basically we have a hanging basic application. So jump is, well, it's a go-to in basic. And the star means the current address. But generally, this is the cleaner approach. Return back to basic. And here you see that is that basic upstart generated that first line 10 sys 4T96. 1000, that should be it. Yeah, that is 4K. Yeah. So that is basically what this basic upstart filled in for us. So if you type run, it will just run it. And we can prove that again. Let's make it a C, just for clarity's sake. Sometimes it is not quick enough with compiling, or it runs old code. Come on, come on. Or is it because this one is still there that it cannot write? I think that was the problem. If you forget to close a screen, it will probably lock. No. Hey, why is my... Oh. Everybody was already yelling, you're still using the kernel call. I did not see that. So there we go, yeah. And if we just run it again, yeah, run again, you can see that list with this command is actually running this, which does the same thing. And that is what the basic upstart fills in for you automatically. Saves you a lot of time. So that is the first C64 entry into programming, and we already covered a lot. We covered the accumulator, the X index, we covered storing the accumulator, and basically all the other commands are sort of variants on this. So if you grasp this, then the next lessons that will pop up later on will be a cinch. So there you have it. We already did a lot with C64. And basically all the other commands that you use are variations of what we already did here. So as you can see, it's not really that hard. It's understanding the memory map and the C64 specifics. The 6502 assembly is really, really easy. So in the next one we will probably dive into the stack, because that is important if you want to create good, proper, clean subroutines. And that's also what I tend to do in this video, is actually learn you how to use subroutines, make cleaner code, because all the other tutorials I saw is just big chunks of text, and yeah, it will work, and often it's efficient, and sometimes you need to save those cycles, but generally you don't. Generally, more legible working code is more important than high efficient code, and that is what I try to teach you here as well. So I hope you learned something, and see you in the next one. God, it's hard.